Hello, everyone. Thank you all for coming. This is the first talk of our Saturday Engineering for Everyone seminar series. This is a series organized by the Department of Electrical and Computer Engineering. Thank you all for coming on such a short notice, I guess. I'm delighted to have our first speaker, Professor Naresh Shanbhag. He's a faculty in the Department of ECE. He will be talking about many things that he has done over the past 20, 25 years. So please give him a warm welcome.
Thank you. Thank you, Pawan. First, I want to thank all of you for coming here on a Saturday morning to attend this talk. This is a lecture series that we organized, the EC department, for many years. And this year, it's Pawan Hanumolu who is the organizer of this lecture series. We'll have two more later in the semester. The first talk will be, I'll be giving the first talk, and I also want to thank Pawan for inviting me to give this talk. So as you can see from the title of the talk, in today's talk, I'll describe how we can bring AI to a microchip near you. Now, we all have seen AI being deployed all over the world, all over in our lives, but the brains of the AI today is residing in a data center. And I don't go to a data center, you don't go to a data center, but we still sort of benefit from that connection between a huge warehouse sitting somewhere and our cell phones. So my talk is going to describe how we can bring the power of AI down into our own devices, our cell phones, laptops. Now you might say, why do I need that? Because my cell phone is already very smart. After all, isn't it called a smartphone? No, the smartphone is not really smart. It derives its intelligence from the cloud, from the data center, right? If you cut the internet connection between your smartphone, if you just remove the internet connection, it quickly becomes dumb, right? So in this talk, I'm going to show you how the power of AI can be brought into the phone. And why is it hard? It is hard because AI consumes a lot of energy. And we know our cell phones, they have a battery, and battery have limited energy, right? So how do we bring in intelligence into our devices when I have limited energy supply? How do I pack in intelligence into a small form factor and derive benefits from it? So native intelligence, we want our devices to exhibit native intelligence. Today, they exhibit derived intelligence. They derive it from the cloud. So AI has really taken over, not yet taken over, but it's slowly starting to take over a lot of these social systems, a lot of the social products, activities that we engage in our daily lives. And these are few of the examples. Autonomous vehicles, we have heard some not so good news in recent times about autonomous vehicles. But this is one of the applications that technologists are looking at. Robotic surgery, can we take certain tasks, surgical tasks that are sort of well-crafted, well-described, so that you can tell a computer how to do it, right? So computers are wonderful when you can describe the task in a set of simple steps, multiple steps. Then it does a great job. But if there is some unpredictability, just as in case of an autonomous vehicle, if there's some unpredictability in the environment, in the data it sees, then things are not that predictable. Just as us human beings, we are not that predictable all the time, are we? Computer vision, in fact, the next lecture by Professor Alex Schwing will describe how AI is being used to make computers recognize objects. So you take an image, take a photograph of this audience, and you want to recognize my grandma is sitting there, right? For us, it's easy. I can recognize my grandma very easily, and so can you. But for a computer sees only numbers, all right? Just a bunch of digits. And from that bunch of digits, it has to figure out, that's a cat, that's a dog, and that's my friend. Recommendation systems, we have run into it quite frequently. You go into Netflix or Amazon and you buy something, and the machine tells you, oh, you like that particular cell phone, maybe you would like to get the case for the cell phone. And these are all these different choices. People like you who bought that cell phone also bought these other accessories, right? So this is called recommendation system, and behind it is machine learning. Behind it is a computer trying to guess what you want, okay? So that's what we see today when we think about AI. There are many more examples and many more applications, but all of these applications today run in the cloud, and that's because AI is quite expensive. And here is another situation, another set of tasks which have attracted a lot of attention in recent times. So the previous slide showed you good stuff, it's like use of AI in our daily lives. Here, the researchers are asking the question, how smart can a machine be? Can a machine, if I give it enough resources, enough data, can they actually beat human beings in certain tasks? And the answer is, if you narrowly define the task enough, you give it enough compute power, right, enough data, then machines can come very close and even beat human beings. Here is one of those tasks. It is the task of playing the game of Go, right? You have heard the game of chess. We all have played the game of chess before. And we also know that a computer had beaten the world champion, Garry Kasparov, many, many years ago in the game of chess. Compared to the game of chess, the game of Go, which is like a Chinese checkers, Chinese chess, it is exponentially more complicated. There are many, many more possibilities in the game of Go. And a computer cannot try out all of them and then say, okay, I'm going to take that step, and then the opponent takes that step, I'll kind of follow a decision tree. This type of thinking that existed before cannot be used by computers. Computers have to use statistics, they have to use some prediction, they have to think a bit like a human being if they have to compete with humans in the game of Go. And so this was a competition that was organized by Google Brain. It's a unit in Google. They use their machine called AlphaGo. They build a machine specifically to compete with humans in the game of Go, right? And this machine was trained. They actually showed it, gave it all the rules, number one, and then let it train by playing with real human beings and also with itself. And they could see over a period of time the machine getting better and better and better. And eventually there was a world championship, two of them, one with the world champion from South Korea. And if you read that, the world champion confidently predicted he would win 5-0 or 4-1. So it says he was right about the score, but wrong about the winner. That's what is written at the bottom, right? So it was a total big splash, big surprise. A human being on a very complex game of Go was beaten by a machine. And then later, that was in 2016, it says March 19, 2016, this was in 2017, last year. This was another game in which handily the human champ was defeated. So what this tells us is that machines are getting more and more powerful, more and more smart. And now the big question is, why don't we see all of that smartness? How do we use that smartness, number one? And number two, why isn't my cell phone that smart? I can't talk to my cell phone. It's just if I remove the internet connection, it's just a very quiet display device. The answer is, of course, that there's a huge energy cost, right? You can estimate, if you look at the AlphaGo machine and look at the human brain, a typical number for the energy consumption, the power consumption of the human brain is about 20 to 40 watts. Compared to that number, a AlphaGo machine consumes about 10,000 times more energy. So this is not really a fair competition. A fair competition would be one when my cell phone plays the game of Go and beats me at it. And I should be very good at the game of Go, right? So there's still hope for humanity. There's still a gap, all right? But, people like me, when we look at that number, we say, hey, there is some work for us to do. So we are actually trying very hard to build systems, build architectures, build circuits that are going to reduce that gap, because that is the uncharted territory for technologists. Okay? So to summarize then, today AI resides in the cloud, and you have devices that connect to the cloud and derive its intelligence from the cloud. So these are edge devices. We use the term edge to describe them. The data center has unlimited resources, compute resources, storage resources. It is powered, plugged into the wall. In fact, there's a power plant. All these data centers have their own power plant that supply the power. So there's no issue in terms of resources here. Here, it's totally contained. There is a small form factor, battery supplied. Can we bring that intelligence into this device? Right? That is a challenge that we face today, and this is what we'll be discussing, we'll be talking about. So this is an article that just came out last week in IEEE Spectrum that says how we can speed up AI by mixing computation and processing. And we'll see later in the talk that one of the reasons why AI consumes a lot of power is because it has to chunk through a lot of data. And when you chunk through a lot of data, you have to read from memory frequently. And that reading data itself is very expensive. Computation is cheap, but reading data from memory is much more expensive. And so AI applications totally consume that energy budget the moment they start working. So this article, actually I want to acknowledge my students whose work contributed to this article. Minggu Kang was the first student who came up with the idea of what we call as deep in-memory architecture, DIMA. You'll hear more about it towards the end of the talk. Sujan, Minggu is now graduated, working at IBM. Sujan, Amaya, and Sangmin are here. Amaya, yeah, and Sujan is somewhere there. And so Sangmin is in the basement of CSL. In fact, at the end of this talk, Amaya and Sangmin will give a demonstration of one of our in-memory chips, right, towards the end of the talk. So you'll get a chance to break the machine if you can. All right. So it turns out if you want to bring AI close to the cell phone, close to yourself, if you want to remove that physical distance, one needs to leverage all three pillars of innovation and pillars of the information age. And if you were to ask me, when did the modern information age start? It started in the 40s. All the big intellectual advances, jumps that occurred, it occurred in the 40s. And it started off with the invention of the Turing machine, the von Neumann architecture in the world, and AI by certain group of individuals. And then we had a microchip that allowed us to actually build these computing systems in a very small form factor, right? And so with these two innovations, you could implement AI in the cloud today. This is where we are. There's a third major innovation that most people may not know about, and that is Shannon theory of communication. Now, Shannon theory was used only for communicating data, not for computation. So in our group, in our research, we used Shannon theory for the purposes of reducing energy consumption in computing. And so this innovation is what enables us to bring AI in a microchip near you. So now you can tell from here, I want to share with you some of the history of computing. One, I want to share with you some of the microchips, the history of microchips, and I got a number of number of samples here that I want to share with you. And then we'll end the talk with how Shannon theory was used and how do we build AI chips today, right? So starting from the past, we'll come all the way to the present. So let's start off with AI, the AI part of it, the Turing test. So Alan Turing, as you know, is the father of modern day computing. And in 1937, this doesn't show that, in 1937, he described the Turing machine. And then he went on to think about computer intelligence. right? So this paper was published in 1950, and there he was asking the question, can a machine think? Can a computer think? Is a computer intelligent? Can we make it intelligent? Now, the word intelligence is very loaded, right? I mean, how do you define it? What is the metric? Different people have different metrics. It's hard to define. But Alan Turing was very smart. He said, no. Let me say that I'll define intelligence in the following way. If a computer and a human were doing the same thing, and if I were to look at the results, the outputs, their responses, and if I were unable to figure out which one is a computer and which one is a machine, which one is a human, then I would say, yeah, it's, the machine has approached the intelligence of a human being. So Alan Turing took the position that a human being is an intelligent being, and a machine, its holy grail is to approach the behavior and the decision-making capabilities of a human being. Now, human beings make mistakes, and that is fine, that is accepted. But if I cannot figure out which one is a computer and which one is a human, then I would say the machine has passed the Turing test. So his idea was put a human judge, have two rooms. In one, there's a computer, one, there is a human. The judge sends in queries, right? Asks questions, and you get textual responses, textual input, text responses. And based on the response, can the human judge figure out which room has a machine, which room has a human? This is a very simple test. But to this day, the computers have not passed the Turing test. It's very, very hard, right?
What if the reason I know what's different is the computer is perfect?
Well,
and the human isn't.
Yes. So then it's easy to figure out that which one is a computer. Yes. So if the machine pretends.
I shouldn't be able to tell.
Sorry?
The test is I shouldn't.
Exactly. So being perfect, if that is the definition of intelligence, this is not what Turing described. His view was that if you become perfect, if the machine is perfect, then its capabilities get limited. And so this is where us as humans, when we think about ourselves, the fact that we sometimes make errors, but also those errors help us learn, adapt, and become creative, right? Those are the attributes that he wanted machines to exhibit, right? And so it's very interesting that this term, the imitation game, was used to describe the Turing test. But how many here have seen the imitation game? Was there any Turing test in it? There was no Turing test, right? So it's a mislabeling of a movie. The real imitation game is the Turing test, and this one was one of Turing's, the breaking of the Enigma code was one of Turing's, what I would call as lesser accomplishments. Though he saved the world, I mean, he broke the Enigma code, helped the Allies win the war, but in the larger context, he also established a foundation of computing. He also established a foundation of artificial intelligence. And so we are all beneficiaries of his work. So if that is a very hard test, researchers said, let's, for machines to pass, if that was a very hard test, let's simplify it. The simple test is, there's a cat. This is my own pet. His name is Tiger. All right, you'll agree he's cute. On the left, and then on the right, is that a dog or a cat? Dog, right? I mean, it's sort of dog. We know it's a dog. But believe it or not, for a computer, because these two look so similar, a computer, it can make errors very easily. So in these cases, what a computer sees are a bunch of numbers and a bunch of numbers there, and it has to figure out, if that is a cat, that must be a cat. I mean, that's a much natural thing for a computer to do. However, and so the world of AI started simplifying the tasks for which you can design machines. And then, only recently, in 2015, in terms of image classification, so you have a database of images, and this database is called ImageNet. There are 1,000 classes. 3 of them are shown here: person, dog, chair. For the first time in 2015, they were able to design a machine that could beat a human in the recognition task, right? So this is it's a very recent development. But the task itself is very simple, just recognition. It's not about learning. well, there's learning underneath it, but it is a very well-defined, precisely defined task output, right? So this is one development that occurred not too long ago. And so a little bit of how that machine classifies tasks. Basically, if you and I were to look at a cat, we would say, well, we won't think like this. We'll just say, that's a cat, that's a dog. But in our brain, what our brain is doing is looking at certain features of the cat. It's saying, oh, that looks like pointy ears and whiskers and sharp mouth. Eyes are spread out. OK. I mean, this our brain is doing automatically. So for the machine to, what we need to do is extract features of the image, so shape of eyes, shape of ears, and together, hopefully, in the feature space, you can separate the cat, the class of cat, and the class of dog. And so there is a separating decision region, which the machine has to be taught. The machine has to learn, given the data, that all of these features belong to the cat, all of that belong to the dog. Now, occasionally, there will be certain images, like the one I just showed you, that is very close to that to the boundary, right? So sometimes machines will make errors. They might, if this line was slightly on this side, if it learned a wrong or a different line, then it will make errors, right? So at the end of the day, this task is called classification. It's a very popular machine learning task, and all of us are working hard to improve its accuracy, number one, and the energy efficiency with which we can make these decisions, right? This is a very basic, fundamental building block of artificial intelligence. All right. Now, inside that machine, you have a feature extractor. Ears, pointy ears, whiskers, those are features. So the first step in that machine is actually to extract the right set of features and then be able to find out that separating line that separates the world of dogs and the features of dogs and features of cats. And so all of that has to be learned by the machine, right? So there's a trainer sitting up there. And just like when we were young, we had our parents tell us, that's a cat, that's a dog, right? That we were trained to label things as we saw it. Similarly, machines have to be trained. There's always a training phase, and the training phase needs a lot of data, right? We are continually learning. Human beings are continually learning from their childhood. And then once that's done, you have to test it, right? So when you become teenagers, if the training was good, solid, when they grow up, they make the right decisions, live a good life, and so on. Same thing with machines. If you have trained it well, then when you give it a new set of data, which is called the test data, it will work better. It will make right decisions. But it will never make perfect decisions, just like us, all right? Okay, so inside of the machine, and inside of the AI machine, there are lots of, basically it's a bunch of multiplications and additions, which we all know from middle school or primary school. We know how to add and multiply two numbers. Well, an AI computer, AI machine is doing a lot of it, a lot of data, multiplications and additions, and then at the end, you look at the final result and say, oops, I think this is a dog or it is a cat, right? That's at the heart of it. And to implement these multiplications and additions, you need a computer. And this is where the work of Alan Turing shows up again. So even before he talked about AI, the first step was he proposed in 1937 a machine called the Turing Machine, right? And this was Alan Turing saying, what is the simplest computer I can build? What is the most abstract, simplified description of a universal computer, a computer that can solve a huge class of problems? Von Neumann in 1945 came up and said, oh, that paper was a splash. It made a big, huge impact. But nobody knew how to build it. Von Neumann showed up in 1945 and proposed a von Neumann architecture. And today, all our computers, whether it is a laptop, cell phone, the chips, the computers that sit, computing engines inside these devices, they're all von Neumann architecture and they're all Turing machines, right? So this work that was established in the 40s is still being used today. And you'll notice something. There is a separation of memory from computation. That's memory, that's computation. That's memory, that's computation. It is fundamental. It is how we think about building computers. You store something here, and then you read from it data, and you compute somewhere there. And this separation in the world of AI today is hurting us, hurting in terms of energy efficiency, because you have to process a lot of data all the time. So this traffic kills us, right? And this is at the heart of the work that I'll talk about, the work in our group, which is to eliminate this separation between memory and computation. Okay, so having said that, the impact of to build a computer, you have choices. In the early days, we used vacuum tubes, and your computer was one big room. Today, we use a microchip, and more power than this computer is sitting in our hands today. So the microchip has truly revolutionized information technology, right? The reason our cell phones are small and powerful is because of the microchip. Compute power has increased exponentially. So that brings me to the topic of microchips. What is a microchip, and how is it so great? Okay, that's the microchip is built using small switches, and the switches are called transistors. And in fact, there were three individuals, John Bardeen, Walter Brattain, Bill Shockley, who got a Nobel Prize for the transistor in 1956. All right, and in fact, the first transistor, that picture you see there, I have it here. I have a copy of that first transistor, courtesy one of my colleagues, John Allen, who used to work in Bell Labs. And through his connections, he has gotten a real transistor, which I'm going to put up there. Later, you can take a look and try to remember that triangular piece of material wedged in. That wedge is what gives it the transistor property. So this is sitting here. I have only one request. Please look, but don't touch. All right, it's a very, very valuable artifact. There are very few places that can actually boast of having the world's first transistor in their organization, right? So, and this is with the EC department here at Illinois. And furthermore, there's another strong relation between us and the first transistor. John Bardeen was a U of I physics and EC professor from 51 to 91. So the inventor of the transistor came to Illinois and spent his career, last part of his career, in our department. Now, a switch is good, but not enough. You have to put millions, billions of those switches on a single substrate, right? In order for them to work, do something useful, you need a billion of them. So how do we take a billion of those transistors and put it on the same substrate? That entity, that result is, that object is called an integrated circuit. And Jack Kilby, he got a Nobel Prize in 2000 for inventing the integrated circuit. He has a co-inventor, Robert Noyce. He was our alum, right? 1947, he got his bachelor's from this very EC department. So our department has a very strong connection into the world of semiconductors, and we are all very proud of it. Okay, what did the microchip do? You can see what it did. It took this big object and made it small with more power, more features than what the original cell phone had. But interestingly, after it went down, it's starting to go up again, right? Because people are trying to make it smarter, and if it is smart, it has to display many, many things to you, many different types of data. So it's becoming bigger and bigger. Now, our goal is to sort of pack in as much intelligence, artificial intelligence, into that small form factor. So the evolution of the microchip was, in fact, predicted by Gordon Moore. Gordon Moore is a founder of Intel Corporation, and he wrote a paper in 1965 in which he predicted that, he just predicted based on some recent data, that I predict that in the foreseeable future, the number of transistors will double every 24 months, right? Actually, every 24 months, 2 years, it's going to double. And people thought, why? What is the basis for it? But it became a self-fulfilling prophecy for the semiconductor industry. So if I'm a company in the semiconductor space, I know that my competitor is going to follow Moore's law, so I better do it, right? So that actually energized, created this huge revolution in the semiconductor field. And that revolution is continuing to this day, all right? But it has slowed down a little bit, and I'll explain why. And the impact of that revolution is huge. You have, compared to what the transistors you had in, the microchips you had in 71 to what you have today, you have 5,000x lower energy, 50,000 lower cost. This is why your cell phones don't cost a lot. I mean, they still cost a lot, but compared to what they can deliver, all right, they are actually quite cheap. And this is all because we are able to shrink those transistors, make them small, and yet make them work well, right? So that's called Moore's law. It has been at our disposal it has been serving us for all these years. And by the way, Mark Boher is a leading edge device researcher who's pushing the limits of Moore's law at Intel, also one of our alums. Okay, so now, where is the microchip? I see a cell phone, I don't see a microchip. So I'm going to take a very old, not so smart phone, okay, because that's what I'm going to use. And I'm going to show you where the microchip comes. I'll try out the dock cam, south projector, okay. So before I took off the top cover, it looked like this, all right? It's an old phone, but you can imagine your smartphones are no different. They're just, the shape is different. If you open it up, inside will come out a circuit board, okay? And in the circuit board, you can see those black spots, right? Those, let's see, there's a pointer here. No, I just need a sharp object to point. But anyway, I can just point it here. So this black object is your microchip, right? It is the brains of this cell phone, right? It is packing millions, billions of transistors, doing a lot of computation in that small form factor, all right? So this is what the microchip does for you. It brings an entire computer, entire room that you saw in 1946 is sitting inside this computer. I told you about von Neumann architecture, right? And I said all our computers are von Neumann computers. This is an old Intel microprocessor that was used in the desktops many, many years ago. And if you flip it over, you're going to see two of the chips. So what you see here is the computational unit, the compute part, additions, multiplications, they occur here. And this chip is memory. It's a cache. So it's a huge memory chip that stores data. And if you were to run an application, let's say you run an app on this machine, then the traffic from this memory to this computation is going to be huge. It's going to slow your processing down, number one, and consume a lot of energy, right? And this is what I had mentioned earlier, that in a von Neumann architecture, there is a separation between where you store data and where you compute. It is from the origin, from 1940s, they proposed a separation, and then the circuit designers, chip designers took that separation, realized it physically, right? And today in the world of AI, that separation is the cause of the high energy consumption and latency. The response time is reduced. All right, so that's an example. By the way, all of these samples are up here. You can, after the talk, you can come up. All right. So then, if you opened up your cell phone, you'll see the circuit board. You'll see those chips. Those are called packaged chips. Now, if you open up the packaged chips, and in the Intel part I showed you, there is something called a die, all right? It's called a die. It's actually a piece of silicon which is patterned. And the pattern captures the connections between the transistor switches to do some useful computation, all right? And that pattern, that die, is actually part of a large wafer. And I will show you one sample here. This wafer is made out of silicon, and there are many parts, many dies in there. So when you go to Intel or when you go to TSMC, they will fabricate, stacks of these wafers in one shot, and then at the end they'll dice it. And so producing that smart microchip in large volumes is very easy. Well, it's easier said than done from an Intel perspective, but it can be done once you have all the manufacturing issues addressed, then it becomes easy, right? So producing microchips in volume is what makes electronics cheap. It is what has brought microchip into our cell phones, into our laptops, right? All right, by the way, you can always stop me, and if you have any questions, feel free to stop, all right? So that's the wafer. Now, if I zoom into the die itself, now I have that piece of silicon, small piece of silicon, I zoom in and look at it, then what will I see? I will see a layout. It's like a beautiful, nice puzzle, different colors. Each color represents a particular material that are stacked together to design the microchip. And so when we design microchips, as my students do in their lab, they have a workstation. They sit at a workstation and they draw those patterns. All of these patterns they draw. Before drawing that, they have to know what pattern to draw. So most of the thinking goes in designing the requirements on those patterns. And then we send it to one of the factories, foundries we call them, that manufacture those dies for us, send it back to us, we get it packaged. And of course, we don't sell it, but we test it, and then we write about it. But there are some professors who might actually build a company, a startup company, and then sell it. And there are some of us who do that. All right, near you part, right? So now you know that artificial intelligence requires a microchip to be realized, but even today, the number of adds and multiplies is huge. It's hard to bring it near you. So we saw this slide before. We saw why it is hard. It's because our cell phones don't have enough battery life, right? You're processing all of these data in your cell phone. If you try to process it in your cell phone, the battery will die very soon, very fast. So we connect, use our cell phone, we connect to the data center and make it work. So today, AI is in the data center, it is in the cloud. That is what all the intelligence is sitting there. And if you try to bring it to your cell phone, either you need to reduce the sizes of your transistors, you have to make each transistor more efficient. And in the past, Moore's law actually gave us not just reduction in size, but also energy efficiency. For the same operation, add, multiply, they became more efficient as you go from one size transistor to a smaller size transistor. Right. But today, Moore's law is slowing down. Right? So we cannot leverage what has always been at our service, what has always been like a silver bullet to the problem of energy efficiency, to the problem of what we call as integration density, that is taking a lot of computations, packing it down, right? So that those benefits we cannot rely on Moore's law as much. And the von Neumann architecture, which has this separation between memory and processing, computation, that memory wall, which was always there from inception, it is getting worse in the world of AI. AI is stressing that wall hugely, all right? So in our group, we asked the question, what can we do? I and my collaborators, we asked this question, why is it that computation and memory, why are they separate? And how do we operate at the limits of energy efficiency? And it turned out, if you look at two of the systems, one is a communication receiver and one is a human brain. We're all amazed by the human brain. It does so many things only at 20 watts. How does it do it? Turns out, and cell phone is similar, it transmits data from here all over the continent to the other side, and somebody can hear me, I can send data packets, they get it. So much noise, still it works. How come? The answer is that there's an underlying principle, that when you build these systems, you have to work with what we call as stochastic circuits. That is, the building blocks should be allowed to behave unreliably, but we use models of computation. We use our knowledge of what information we are interested in and what is the end user interested in, and use mathematical techniques to compensate for those errors, right? So there is intelligence in terms of designing those algorithms, architectures, but the building blocks, we should not have them be perfect, right? And the reason is, when you build transistors to be perfect, they have to be big, they consume more energy, and they are slow. And today, in the world of von Neumann, we don't know anything else. All we know is take a reliable transistor, build a reliable circuit, build a reliable architecture, and I will get a reliable computer. But that's not how a communication receiver and a brain, which arguably are operating at the limits of energy efficiency, this is not how they work. They, in fact, work with stochastic components. The building blocks are unreliable. Yet, their behavior, the outward behavior, the results, they are reliable, but there's always some error. Once in a while, we allow a communication receiver to make errors, and we also make errors pretty much all the time. The big question is how to do this in a principled manner. And this is where the third pillar of the information age comes in, Claude Shannon. It took him about 10 years to write this paper in 1948, and his paper revolutionized the world of communications. So we talked about computing, von Neumann, Turing. The world of communications is totally built on the theory that Shannon wrote about in 1948. The more important thing here is that it has statistical foundations. Unlike a von Neumann architecture or a Turing machine, the principles of reliable data communication is built on statistics from day one. But people who build computing systems don't leverage this foundation. They have not leveraged it to this day, right? In fact, von Neumann himself wanted to do that. He wrote a paper in 1956, and that paper was making the assumption that your circuits are going to be unreliable, all right? They'll make errors, and how do we build reliable systems with unreliable components? And he said, my work is rather unsatisfactory and ad hoc, and that we should use Claude Shannon's ideas to build computing systems. But it was very hard. It's very difficult to use a totally different way of thinking and a different way of designing systems. So this is where sort of I want to give you a flavor of my own research. When I came to Illinois in 1995, the senior faculty in this department said, Naresh, do something great, all right? Don't do the same thing you did in your PhD. Everyone else can do it. Try to come up with some really innovative ideas. And I took that to heart, and I said, hey, I've been thinking about Shannon theory and its role in computing. So this was the first paper we wrote in 1996. And this was more of a sort of an aspirational paper. There was no big solution in there. It was just a position paper that says, we should think differently. And then since then, a number of researchers from 96 onwards to this era, to today, we're kind of building upon that particular foundation. In 2010, I just realized when I was preparing this talk that we also had an article in IEEE Spectrum, which, as I said, is very broadly read. And it talks about our work in developing this Shannon-inspired perspective. Okay? In 2013, our work was recognized, and we created a center called the Sonic Center. In fact, Professor Malu was a member, because we wrapped up our activities in December 2017. And the center brought in a number of faculty and students from all across the United States to build up this Shannon-inspired framework for computing. And the sponsors actually looked at us and said, you are the guys who ought to be leading this effort. And they funded us very generously over the last 5 years. And that's our team. We are the lead university, the lead department, the EC department, and we can see a number of our faculty from Illinois who are in the center. So what did the center do? We developed fundamental principles, we came out with architectures, and then we built prototypes. We showed that these Shannon-inspired ideas, where you build a reliable system with a stochastic component, is actually real. And one of the stochastic components is a deep in-memory architecture, right? So remember, the memory wall is the killer. Why didn't people break it down earlier on? Why? Because memory is typically analog and computation is typically digital. And if you make an analog is stochastic, it is not very reliable. I don't know if Pawan will let me say that, but it's much easier to build digital circuits that are predictable, that are deterministic. But they are very expensive in terms of, they're separated from memory. So a lot of data has to flow from this analog to digital. So what we did was to bring computation and plump it, put it next to the memory in analog. So, and we did it in such a way that the unreliability is managed so that you don't see it. The user will see decisions being made by this computing engine that is reliable, right? And so this was the first paper we wrote in 2014. And the best thing about this patent we got, can somebody tell me what is the most attractive part of this patent? July 4th, 2017. So we had more than one reason to celebrate last year. And this patent is very broad. This technology is is going to become very pervasive. You saw the article that I showed you earlier. And so we're very happy with the outcomes. In our group, we produced 3 chips, each showing that this idea of deep in-memory architecture is real. And we have tested it out in our labs. And in fact, right now, we have Sungmin sitting in CSL, who is Coordinated Science Lab is the building right across the squad, and he's in the lab downstairs. Amaya will come up and show us a demo. And let's see if we can break this chip. All right. You need this?
Yeah. Hello?
Yeah, it's on.
Okay, now
You should bring up your mic a little bit up. Yeah. Okay. All right.
Okay, so now is the fun part where we show one of our chip actually working and doing some intelligent tasks for us. And so on the screen, on the right side of you, you see a scene from our lab. And this is the lab where we actually work, and this is the desk. And I see there are a lot of equipments there. This is where the microchips that we build are tested on this table. And we want to focus on 3 important entities. So there is a power supply, there is a computer, and then there is an AI microchip that we built. And so the AI microchip that we built needs some energy to operate. And so the power supply is giving it the energy, and the computer is giving it commands and giving it inputs. So via computer, we can control what that AI microchip should do. We tell it that, okay, classify this image, or do this task, etc. So there are these 3 things, and this is the whole setup. So now Sungmin is there.
Actually, there is a 4th entity.
Yeah.
Sungmin.
Sungmin, yes, okay.
So the student, he is inside there, and
Yes.
Sungmin, can you say hello?
Sungmin? Okay, he has to rotate the camera. Okay.
All right, that's believe he is one of our team members. All right,
Yes,
go ahead.
correct. Yes, so he's a cameraman there who is going to walk us through the setup.
All right.
So Sungmin, now let us see the AI microchip more closely. So yeah, there we go. Yes. It's almost like a movie. So here's the AI microchip. The green part is the board that we designed, and there is a pointer somewhere.
Yeah.
Yes. So this metal socket, our microchip is inside that socket. So it is very tiny. It is just 1 mm by 1 mm. It's a very small piece. And that piece is sitting inside this, and we need a good socket to keep it in place and secure. And this board is basically surrounding circuitry that can give its inputs in the right way and make sure that the supply, voltage, currents are all flowing perfectly. So these are the surrounding circuits, and this is the board, and the chip is inside. Okay, so now we can take a look at power supply maybe, Sangman? Okay, so there we go. Yes, and so this is the power supply, and on the left side here, we have an interface, which allows me to control some numbers here, which will get reflected here. So I can show you, for example, if I change this supply voltage to, say, 650, then it will change. Okay, it's not visible. Okay, it's one of the things we get excited about, but it's not really visible here. But so the bottom line is that I can enter some numbers here, and they get reflected here. And this is the remote screen of the computer. So Sangwin, can you see a computer? So there is a computer there, and we have brought that screen up here so that we can put some numbers in and see how it is running. Okay? So now we move to the left part of the screen where I have an interface. And unfortunately, the microchip doesn't show that it is running. It's just sitting there. But okay, so now on this left side, I have an interface where I can select an image. Let's say I select some image, I don't know, maybe 645. Oh, no. Okay, and then I press, wait, let me reset it first. There we go. And then I press 645. So this task is traffic sign recognition. So all of us are familiar with the traffic signs. And if the self-driving cars need to come up, they need the ability to recognize the traffic signs. It is a very fundamental requirement for a self-driving car. And so our microchip is able to recognize the traffic signs. And so on the left side here, I have selected one traffic sign. All of us know, hopefully, that it's a parking sign. And now I select the number of classifiers. It's the strength of my classification system. If I choose maximum 42, many of the classifiers will work together to recognize this image. If I select lower number of them, only few of them will work to select this image. And then there is a supply voltage where I control how much energy I want to spend to recognize. And now let me select this. I select this. Okay, now let's run, and hopefully it is correct. It's running. It takes some time to take this input, send it to the chip. Okay, parking. There we go. So there is Dima's answer here.
Oh, wow.
Parking.
I'm glad.
Okay, yeah. Okay. Oh, okay. So actually the chip is making that decision within nanoseconds, few nanoseconds. It's that our interface is slow. So in the demo, it is running because it takes some time to take the image from computer, send it serially to the chip. But inside chip, it is making those decisions within nanoseconds, few nanoseconds. Okay. So now, do we want to try a different image, or maybe? Okay. So Professor Shanbhag mentioned, right, one thing. Let us see if we can break it. Correct. That would be interesting. So I reset it. Exactly.
Try a small number.
Yes, I can try small number.
That's a good suggestion.
Classifiers.
Break it.
Yeah, so this, if I select small number of classifiers, let's say just 4, and I press enter. Let's keep the supply voltage for now. You can see the energy is lower now, and if I run now, let us see what happens. It's running. Okay, it is still correct. I mean, we designed a good chip. But
or the data was very easy to, it's pretty clean.
Yes, that is
easy to recognize.
Yes,
so do you have a hard data?
Yes.
So, can you throw a random image and recognize something?
Sure. Oh, okay. So this microchip is trained to recognize traffic signs.
Okay.
Okay.
Random parking sign
You could do that.
You could. So,
So in fact, what I would say is that those 690 images, you can view them as like a huge collection.
yeah.
And you can randomly select any of. So randomly select some other
Yeah,
harder,
so you
harder
can
image.
give me a number.
You can go on Google and grab some
Yes.
parking image and put it there.
Yes.
Are those
Sure.
Are those 690 signs the ones that were trained on?
No. They were trained on a bigger data set. That was not
Separate.
part of this 690.
Yeah.
This is a test data set. So these 690 images, the chip never saw it while training. But it saw similar images. It still saw traffic signs.
So remember, there was a training phase that is done with a totally different data set. All of these 690 images are new as far as the chip is concerned. So randomly you can select one.
Yeah,
Just select
give
a
me a
hard
number.
one. Why don't you go ahead? Yeah, 512. I don't know.
Okay, we get
84.
84. Okay, let's do it. Okay, I reset it. It was 84.
Okay.
Okay, so it's a school sign. Okay, let me first make it 42. And then let's say this is 650.
Make it smaller, or let it be, yeah.
Yeah, so
Then we'll break it. Let's see what happens now.
Yes. Oh, okay.
So there's a question here.
Yes.
Why can't, yeah, go ahead.
Why can it use a minimum number of classifiers? Like go through and go, okay, these are the best ones to use. I only need 4. Got it. I'm
I
only
see.
using 6 here.
Yes.
Instead of using all of them.
Yes. So some images are harder, as we saw in the lecture. Some images are harder to classify. Some images are easy. So for some images, 4 classifiers would be enough. But for some of them, we actually need all 42.
But the question is it smart enough to decide
How many you need?
when to stop?
Oh,
Yes, that's
so-
a very good question,
Yes.
right? I mean,
That
how,
is
how
a-
do you decide the right number of classifiers?
So we believe that if you want to, if we consider all the images, let's say there are all possible images, if you want to be right, let's say 99% of the times, most of the images, then we need 42. For some images, we may need smaller, but we don't know beforehand whether that's an easy one or a difficult one.
But I would say that if you were to build a smarter chip, then
Yeah.
what it would do, it would actually look at the kind of images coming in
Yes.
and then tailor, it'll reduce the number of classifiers in real time.
Yes.
And then reduce energy that way. So that's actually very good.
Observation,
Yeah, good observation. And in fact, that's an add-on. It's more of an adaptive system.
The 40 counts for 10 times as much energy.
Yes.
Correct.
Yes.
Exactly.
Yes.
Exactly.
So now we can break it maybe.
Yeah, why don't you quickly break it? Yeah. Sir?
Did you build this to cheat the captcha thing?
What is it?
Verification?
What is it?
No, so yeah, I'm sure people are working on building these such things to break the captcha, but then captcha also gets better. So
Captcha. Okay.
yeah.
If it comes up with the wrong answer, does it learn from that?
If you take the result of that wrong answer, so the question was, can it learn from its mistakes? And if it knows it, so right now, this machine may not know it made a wrong answer. It gave an answer. But if you were to tell it this was a wrong answer, you can use that information to train itself to get better.
Well, it seemed like to me the true intelligence would be it determined
Learning.
on its own.
Correct. So true intelligence would be one where this training and testing is all happening at the same time. So it is always making decisions. In the beginning, it makes a lot of errors, and then slowly it gets better, right, on its own. So that's called unsupervised learning. And right now, we are in sort of the supervisory phase, that you do supervised training, and then you do testing separately. But in real life, you want it to actually learn as it goes along. So that's a good point. Yeah, that's a very good point. Exactly. So right now, think of it as a static design. We are sort of studying, what is the energy versus accuracy trade-off. And if I have to rebuild it, if I have to actually build a real good design, I would take that curve and figure out, right, how many classifiers are needed for what data set. Absolutely. That's more of a reconfigurable, adaptive designs that we need to have in the future. Yeah. Yeah.
Let's take a computer with the road things you're looking at. The human brain has emotions for that. Let's say a dangerous thing, a train crash is face coming, and you have intelligence going on, can it recognize fastest enough and give you a warning to the point that that sign should be recognized immediately given a warning? It is going to classify all the signs equally, dangerous, like not dangerous. So my question is, like, emotional, human brain is able to use the emotion to recognize quickly and react. Can we get to the computer to that level?
So basically, can we jack up the accuracy based on the situation, right? That's your question. What do you think, Amaya?
So I think surely. So currently we are just seeing an image, and so the system only sees an image. But as you see, humans are more aware of the context. Like I can hear a sound. I can hear a sound of train coming. So I probably see that I can expect some train sign there. So of course the chips can also be aware of the context in which they are operating, and that can help them to make the better decisions about the recognized signs.
Another way to describe it is, right now we're only looking at images. So that's one data mode, right? That's one sensory mode. But you can have a multi-mode sensory chip in which you look at temperature, pressure, audio, video, right? All at the same time, fuse the inferences together, then make one decision. So this is how we work. We have multiple sensors, and then we take it from all those different channels, and then we make a decision. It can be done. Right now, this is just looking at one channel, one video stream. Yep. Yes?
Does each microchip have to be trained, or can you train
Very good question.
a smart one and then it trains all the new ones?
Okay, so the conventional way of doing it is that you train every microchip separately. But researchers are working on exact same approach that you described, that you train one gigantic smart one, a bigger one, and it trains the smaller.
Actually, if I may, can I switch that to the previous one, that slide?
Oh, sure.
Can I go back?
I think this will.
Yeah.
Yeah.
Yeah, so no,
Okay.
sorry. Just one slide back. So if you look at the rightmost chip, what does it say? On chip, learning is doing that. You can put learning, the rightmost chip actually learns on chip. So the data comes in and it trains itself. And so the parameters, each chip will be trained uniquely with the same data. Right? So you are way ahead. That's a good question. The chip we are showing you now is the one in the middle. It doesn't have the on-chip training. So if I take a different die, a different piece of silicon and put in the lab, and when I train it, its behavior will be different from the behavior of the chip that we are showing you now. But statistically speaking, if you do it right, they will all behave similarly. That is, their accuracy will be similar.
Where does your training live right now? Is it on that chip or it's in your computer?
This is the chip that we are testing, so you see that there. So this is being done offline, right?
Yes, this is offline. So this is offline. We have trained it using computer offline, and right now there is no training. It is just producing decisions based on what it has learned.
So right now when you test it, you send in like a set of images it never saw, and then you see what results it produces.
But training is changing something somewhere. Is it changing something
on the chip? That's right.
Yes.
That's right.
Yes.
Remember the training phase? When the chip was a baby, we did the training phase. Now this is a teenager. And now we say, okay, you have learned.
Are your different samples the same enough that they can all use the same training, or does it depend on the actual statistics of the circuits on each particular sample of the chip?
Oh, right.
No, because we have trained it for traffic sign recognition. So we have, in the training phase, the chip has captured the overall.
That is statistics of data. Your question was statistics of the chip itself, right? For that chip. In this one,
no.
In this one, it is not. So this chip, that's why it is our second to last chip. In this chip, we are training it in one shot offline, and then all other chips are going to take the same parameters. But then we realized, hey, that's not a good thing, right? We want the training to be chip specific. And this is where this last chip, which does on die training, it is now learning in a chip specific way. So that's the future. In the future, we don't want training to be done offline. Yeah, question?
What's a microchip in a quantum computer?
That's such a great question. In fact, we are asking the very same question in our department, quantum computing and its role in ECE. In fact, Um, right now, the microchip in a quantum computer, we don't know. I mean, right now it's a big, gigantic piece of gadget that has to be super cooled. You can't actually use it. In the future, what will happen, it's hard to predict. We need a lot of device innovations. A lot of the device physicists have to work together to create a transistor equivalent switch that we can call a quantum switch, right? And it has to be mass produced. Just like the silicon chip, we can mass produce it. Until that happens, that the research, it's a research topic, and a lot of researchers are working on it. How will it look? I don't know. I don't know how it will look. In 10 years. In 10 years, we'll have a better answer. But so far, with silicon, silicon has a huge life ahead of it. Yep.
Will it look like two different things at once?
Could. It could. It is playing with quantum effects. Yes. One more? Yeah.
On the slide you have up there now, can you show us where the processing and memory are?
Good point. Good point.
Oh, okay.
Yep. So I don't know if the lights can be dimmed a little bit, but you see this SRAM bit cell array? All right, this part here. That is where we store. That's memory. Then processing is right there. BLP, CBLP is actually making decisions. So the computation is occurring on that strip, this strip, and then it's converted into digital. Remember I said we compute in analog. That's what makes it stochastic. And then the ADC produces decision at the output, and then we look at it on the computer. So computation is this part, the memory is this part. And in typical AI systems, your memory will be gigantic and computation will be a small strip. So that's why we have to optimize this interface between memory and computation. Yes.
So, is it have any commercial application other than artificial intelligence? Because it's mostly you're integrating the memory and computation in one device.
IoT. So what are the applications of this? You can plop it into any sensory device, any device that has sensors in it. Your cell phone has a video camera, right? It has audio. So those sensory data can be processed locally, and then the cell phone can make decisions on its own. It can decide, it can figure out where it is, what it needs to do, what do I need. So IoT applications, Internet of Things, that's a big one. In fact, right after our article was published, I got a call from a Silicon Valley venture capitalist. Are you guys thinking of a company? All right. So if you read that article that I showed you, IEEE Spectrum, the application space is bringing AI into our surroundings, into the ambient space.
Is this presentation available online? The presentation that you are sharing?
We can make it, yep, we can. I'm not sure if the video is posted. Yeah, that's right. Thank you, Bill. The video of this talk will be posted. Yes.
So I see like the AI chip output selector and the English word. So how is that like related to like the training and study? Is it all done in like how does the chip then?
English is a label, right? I can take one and call it something. I can call it anything. So as long as I have enough number of bits to represent a certain set of words in English, I'm done. That's not the hard part. The hard part is if I'm given 1,000 classes, right? Traffic sign, there are, how many classes are there in the year?
Here there are 8.
8 different
Yes, 8
classes.
classes, yes.
So there are images of 8 different types of traffic signs that are distorted in different ways. And so all I need this machine to do is to tell me, instead of a dog and a cat, it has to tell me this traffic sign, that traffic sign, 8 choices. So, well, it has been trained with a separate data set, right? We don't store the traffic signs on chip. That'll take a lot of space. So it has learned, this is why it is called AI. It has learned that if I get a database of traffic signs, this is how I should look at the features, this is how I should make decision, and that is what is inside the chip. How are we doing on time? By the way, we'll be here right after the talk, so we'll take one more and then we'll quickly wind up, but Ameya will be here, Sangmin will be here at the end, last one, yes.
Was the recent test
I want to get to that. In fact, that's a good point. I do have some warnings. That will be the last part of my talk. So why don't we wrap up?
Okay. So
And let me answer that question towards the end, because that's a closing thought that I wanted to end with. All right. Okay. Thank you. Thank you, Amaya.
thank you.
Your mic, unless, yeah. Okay, so the future, where will all this go? Kind of segues into the question that was asked. If you think about the power of AI, right, and if you can bring AI into a small form factor, you can build autonomous agents moving around, sensing their environment, interacting with humans, making decisions. So right now, our goal is to build machines that think like humans, seamlessly engage, and see this word, co-evolve. If a machine is in your environment, it is actually affecting how you see the world around you. So it changes the way you are evolving, you are growing, right? And we want that growth to be something that is harmonious, that we desire. And it should do it while consuming human level, 20 watts, right? Can we have a 20-watt set of machines all around us that are learning, that are harmoniously engaging us? And this movie, I don't know how many of you have seen it here, all right? I got goosebumps when in the movie there was a dialogue between an intern, Caleb, and the mentor, his mentor, who was inside a lab built inside their home, and the mentor was building a robot, a humanoid robot. And Caleb was asking this question, this is just a Turing test, right? And Nathan says, no, we're way past that. We know that Turing test is so hard, but this movie is making the assumption that, look, we are way past that, and this is why they don't want to hide. They don't want to have the robot in a separate room and the human in a separate room and do a Turing test. It's like, I'm telling you, this is a robot. Now you tell me what's wrong. I mean, doesn't this robot behave like a human being in all respects? Can you see a difference between what I'm telling you is a robot, a machine, and a human being? So that's like the next generation of a test. We are very far away from it. The part that really got me was when Caleb said, her language abilities are incredible and the system is stochastic. Remember, stochastic circuits, stochastic building blocks? I don't know how they came up with this, but you need non-deterministic behavior to actually do something super duper when it comes to AI. AI that operates at the level of human intelligence. We have to break away from the past, the way we did things before. So some thoughts in closing. Today's question that we're asking in the research is, what can machines do? But in private, I asked myself, let's assume I can build any machine. What kind of machines would I like to build? This is the real question that is in front of us. And I cannot answer it as an engineer. I'm trained as a technologist. A lot of my colleagues are. And therefore, engineers now need to work with the folks who are imagining the future. And these are writers, these are artists, designers. And once we get this part done, we can build anything. We should build machines that help human growth, right? It should enable us as a human race to get better, to be safe, to be productive, And that's a very big question. It's about assume we can build anything, what should we build? This is where we are. So I want to acknowledge my department, EC department, our department head, Bill Sanders, is sitting right here. Bill, would you care to? No? All right, Bill has been very supportive of our research, and you can see he's here attending with his family. My collaborators, my students, you saw some of them here, faculty members at UOFI. Pawan is sitting right here, Erhan, I can see there. So it's a wonderful department, and when you come here, you are you're forced to think about something totally unique, totally different. We can't do our work unless we have funding. And all of these government agencies, starting with National Science Foundation, Department of Defense, is a big funder of our research, Semiconductor Research Corporation, the centers I mentioned earlier, and a number of companies. They are all funding that research that you saw today. Right? So with that, I conclude. And